video I'm going to show you how I cut out this Longworth chuck on my laser cutter and fitted it to a rotary axis. I'm also going to make the SketchUp files available for you to download in the description if you fancy cutting out your own. I originally wanted to make a rotary axis for my laser cutter because I started making these bent wood rings, and I wanted a way to cut a design into the ring once I'd actually bent the wood, because it's very difficult to bend wood which is already being cut. However, here is a ring that I etched a design onto using the laser cutter, and of course here's the bent wood object that I etched some text onto in the video introduction. The resolution that I was able to achieve when etching was pretty good. However, when cutting these bent wood veneer rings, I found that the width of the cut necessary to actually cut through the wood made the resolution relatively bad. I'm not sure that I'm actually going to use this device for what I originally built it for. I'm probably going to find some other way to cut designs into bent wood rings. It's not that the resolution is particularly any worse when using the rotary axis, it's just that I think the laser cutter is better suited to making larger objects or designs than those you would find on jewellery. So this is kind of an unsatisfactory video for me. I wanted to not only make this machine but make a convincing use for it, but maybe this is the interesting thing with putting it out for other people to see. Maybe someone actually has an interesting suggestion for what this device can be used for. Of course, if you do have a suggestion, just leave it down in the comments. That'll be quite interesting for me to see. I started with a stepper motor that I had left over from a previous project. It's got a 0.9 degree step angle, and I'd already wired it into bipolar format, and the plug on there is compatible with a normal ramps board pins. This is my laser cutter. I have a video about how I converted it to run on G-code by removing the original control board and fitting in a ramps board instead. That fan you see there is the one that's keeping the stepper drivers cool, and it's fitted onto a customized bracket that I 3D printed when I first converted my laser cutter. It's actually a 24 volt fan because that's the low voltage that's available directly from the laser PSU, but that's not particularly important. Basically, I'm just removing it so that I can get to the pins onto which I can attach the stepper motor, and of course I'll need to attach in a stepper driver as well. Before inserting the new driver board, I installed this jumper to set it to 132 microstepping. This is a DRV8825 stepper driver. It's probably overpowered for this application. You could probably use a less powerful one. And right now I'm fixing it into what would normally be the Z socket on the ramps board. As you can see, the other two stepper drivers I'm using are, I can't remember exactly which, but they're more standard stepper drivers. The DRV8825 is a drop-in replacement for a standard stepper driver. There's my motor. Because it's from a previous project, I've already tested the wiring, and that plug there is just a normal 0.1 inch 2.5 millimeter, that is pin spacing, so that fits right onto the ramps board on the Z axis. Now, before I screwed the fan back on permanently, I just rested it on the board enough to cool the drivers while I double check that everything's working correctly using Prontoface. I did find that I needed to adjust the maximum current available from the stepper driver to the stepper motor to get it to move smoothly. I'm just adjusting that little potentiometer on the stepper driver with the screwdriver, I'm sending long move commands on the Z-axis from front to face, and just kind of adjusting it by eye. There are probably more scientific methods to do this, but I find that this is usually the quickest way. So now I'm sure that I don't need to make any more physical changes to the electronics. I can screw the fan back on and close the electronics panel on the laser cutter. So now I've just got a motor sitting on top of my laser cutter that moves when I send Z commands from front to face. So now it's time for me to make the Longworth chuck so I can actually attach objects to that motor to cut. I chose a Longworth chuck because it seemed to me the easiest design of chuck to actually make on a laser cutter. I wanted a design which would self-center itself, or self-center objects, however you want to say it. It's made of two identical plates with these slots cut into them. The geometry of this looks kind of interesting. I don't really know the theory behind why this design works, but essentially to draw it I first drew these three circles here, and the idea is that the slots are obviously partial circles in themselves, which start on this outer circle and end on this inner circle. Now the radius of each guide circle is obviously twice that of the one smaller than it, and they divide this distance into thirds exactly. The outer circle is obviously just to give some physical structure to this so that the slots don't divide the plate. So that outer circle could essentially be any size. That's not geometrically important. The center of these partial circles is on that guide circle, and that's all there is to it really. I probably could ramble on further, but I don't fully understand the geometry of it myself. I only understand how to draw these guidelines to actually make the circle. So I cut those two identical plates out of 3mm acrylic, and I'm bolting them together using a M3 machine screw. I'm just placing a washer in between the plates before I bolt them together. That's to avoid too much friction when I need to turn them against one another. These smaller pieces are the jaws of the chuck, and I glued those together with solvent cement. Once the parts are bonded, I screwed one roughly 5 or 6mm long M3 machine screw into each. The other screw I screwed into each part was about 25mm by M3. So now it's time to fit the jaws onto the chuck. First I inserted the 25mm long machine screw into one of the slots on the upper half of the chuck. Then between the layers of the chuck I threaded a washer onto that machine screw. Finally I pushed the screws through the slot in the lower layer of chuck and fastened it on using a special sort of nut sort of thing that I cut out of acrylic too. That was just to reduce friction, and also they kind of have a natural locking action onto the bolt that you normally wouldn't get unless you used a nylock nut. Before I tightened each acrylic nut up, I fitted the shorter machine screw on each jaw into the groove on the chuck too, so this would guide the jaw and maintain its angle as the chuck loosens and tightens. I designed the jaws so that they can fit together as the chuck tightens up, and the pieces of acrylic on top of the jaws actually meet over the bolt in the centre so that you can clamp very small objects between them. I think out of this whole build, the chuck itself is the most fascinating object, As I said before, I'm really interested by the geometry of it. I feel like it's just a little bit beyond my understanding. Obviously, I designed this particular version of the Longworth chuck, but it just blows my mind that someone could come up with the actual principle behind this. Next, I cut a couple of circles of acrylic that precisely match the diameter of the motor spindle, so I can just friction fit a kind of mounting for the Longworth chuck onto the motor. I'm gluing this whole assembly together on the motor shaft itself just so that I can get it as centered as I possibly can. We don't know quite how precise it is though. I used a 10mm long M3 bolt to attach the chuck onto that adapter I made, and I wish I could remember to keep my head out of shot. I made a base for the motor which would allow me to raise and lower it depending on the size of the object held in the chuck, because obviously the top face of that object always needs to be in focus of the laser beam. However, the problem is the whole assembly was quite tall, so it was almost too tall to adjust it for larger objects anyway, so I'm probably pretty much going to keep it at the lowest setting the whole time. The most useful thing about the stand is it will always keep the part parallel to the axes of the laser machine because it pushes against the back of the machine. To allow it to fit against that rear face of the box, I had to cut a rough recess in the base part of the stand, which fits over the overlapping welded joint within the box. To use the rotary axis, I'll need to change the steps per unit depending on the diameter of the object that I want to cut. That sounds kind of complicated, but I worked out that that's actually the easiest way to do things. The firmware that I'm using is Marlin, so I'll just have to use that in all the examples that I show. From the diameter of the first test ring that I'm going to cut, I worked out its circumference. I also worked out the number of steps per unit of the stepper. I actually got that wrong because the stepper has 1/32 microstepping, so it has 12,800 steps per unit. I divided 12,800 by 79mm, which equals 160 steps per millimeter. So basically all you need to do is divide the steps per unit of the motor by the circumference and you'll get the value to place into Marlin under steps per unit. That's obviously the value for the Z-axis steps per minute because the motor's plugged into the Z-axis slots on the ramps board. So now I'm going to show you how I cut that text onto the ring at the beginning of the video. I just created this text using the 3D text feature in SketchUp, and I'm going to export it using my own SketchUp to G-code plugin. So just export G-code from 2D drawing and go. However, what I'm going to have to do is change the axes used in the G-code file. I can just do that using find and replace in any plain text editor. And what I need to do is replace the Y-axis commands with the Z-axis commands, and that will just make the new Z-axis that I created rotate instead of moving the Y-axis of the machine. So I'm just going to do find replace, find Y, replace with Z, and then when I save that down, that will run on the rotational axis and the X-axis of the machine. Here's what happened when I accidentally got the text facing the wrong direction. So the longest dimension of the text was actually being cut along the object instead of around it. But as you saw at the beginning of the video, I did get there eventually, and I managed to etch that text around the circumference of the ring. Obviously within SketchUp I had to size the entire string of text to be about 80mm long, so it wouldn't wrap round back on itself. Next I wanted to try using easel to etch an image onto a circular object. So first of all I created this kind of trippy hexagonal based image actually within SketchUp, imported it into easel as a PNG, and then using a process that I've talked about in another video about so-called hacking easel to run G-codes on a Lasercutter, I adapted the text file for the Lasercutter. However, in this case I had to make one other change, which was to use the find and replace to swap the X command for Z commands and the Y commands for X commands. The reason that that's slightly different to the export from SketchUp is that my Lasercutter axes are actually opposite to normal CNC machine axes. That's just the way that I built it, because I didn't know what I was doing at the time. Here's that pattern being cut on quite a large diameter bent wood form. I guess it's about 50mm diameter. You'll notice the pattern is quite stretched out compared to how it was in SketchUp. That's because I didn't bother to change the steps per unit to suit the diameter, because I had quite a few failures by this point in the afternoon. This was my attempt to cut that same pattern onto a piece which was appropriately sized for the steps per unit, the size of the pattern, etc. You can see that it's actually cut right up to the side of the form, just like I intended it to, but for whatever reason this thing just kept bursting into flames. I think if I had time to reflect I could work out an obvious reason for that, but by this point I basically decided that this machine wasn't any good for actually cutting these bent wood veneer forms anyway. Anyhow, I managed to engrave this larger form quite effectively, although you can see that the rotational tracking was drifting slightly off as the cut progressed because the start and end of the pattern moved diagonally along the object. I'm sure that could be dealt with if I really wanted to, but I think I'm going to consign this experiment to just this pile of sort of interesting but not quite resolved things until I can find a really interesting and unique use for it that couldn't be achieved with anything else. And overall I think building that chuck was probably the most interesting thing to come out of all of this. Anyhow, thanks for watching. I hope somebody manages to find a use for what I've been messing around with one day. Please do like, subscribe for more open source electronics, kind of makery sort of stuff. I make videos about Arduinos, including the obligatory Arduino watering system. I modified a Chinese Lasercutter to run on G-code. I started using that to make Lasercut marquetry. I also made a blog about building my own CNC machine from scratch using acrylic sheets and the open build C-beam system. So there's a whole playlist which will kind of show you the process, and all of the designs for that CNC machine are available for you to download, and you can make your own. I used that CNC machine to engrave some veneer to create a replica of the puzzle box from the Hellraiser series of films, which was my entry for the Instructables Halloween contest this year. There's a lot of miscellaneous stuff on my channel, but if you're into maker stuff, you're probably going to find it interesting to subscribe. I'm really happy that I breached the 500 subscriber mark before the end of 2016. and I'm really looking forward to see what this new year brings.